Hey there, and welcome. So, have you ever wondered, how do scientists actually know if a new drug is working, or if one teaching style is better than another? Well, a lot of the time, the answer comes down to comparing groups. And today, we're going to dive into one of the key tools for doing exactly that, the t-test for two independent samples. So here's what we've got on tap. We'll start with why we even need to compare groups. Then we'll check out the tool we use for it. We'll get into this awesome signal versus noise idea, walk through how to actually run the test, and then, the big one, what do the results really tell us? Let's jump in. Okay, so first up, a tale of two groups. This gets to the heart of so much research. The question is pretty straightforward, but it's a big one. How do we actually compare different groups in a way that makes sense? So let's put this into practice. Imagine our producer creates this brand new brain training app. They're claiming it's going to boost your memory. Cool, right? But how do we prove that? We can't just hand it to a bunch of people and ask, hey, is your memory better? We need a benchmark, something to compare it against. This is where the classic experiment setup comes in. You'd have two totally separate groups. Group one, they get the new app. And group two, we'll call them our control group. They'll do something else, maybe read a book for the same amount of time. The really important part here is that these are two completely different sets of people, no overlap. And that example, it perfectly captures a huge idea from the source material. Yeah, sometimes we look at a single group, but honestly, most of the time, real research is all about comparison. It's about asking, is there a difference between these groups? Okay, so we've got our two groups set up. Now we need the right tool for the job, right? The thing that's actually going to compare their results. And that brings us to section 2, where we meet our hero, the independent measures t-test. So this test, it's tailor-made for something called an independent measures design. You might also hear it called a between subjects design. It sounds kind of technical, but don't let the name fool you. It's really just a fancy way of describing exactly what we just talked about, a study that compares data from two totally separate groups. Now, what's really cool is that this test isn't coming out of nowhere. If you've ever seen a single sample t-test, the structure here is going to look super familiar. See, instead of comparing one group's average score to some known population number, we're just comparing the difference between our two sample averages. It's the same core logic, just leveled up for comparing two groups. And like any good hypothesis test, this whole thing is basically a statistical showdown. In one corner, you've got the null hypothesis, H0. This is the skeptic. It's saying, nah, there's no real difference here. Whatever you're seeing is just random luck. And in the other corner, you have the alternative hypothesis. This is what we're usually rooting for, the idea that yes, there is a real genuine difference between these two groups. Which leads us perfectly into section 3, signal versus noise. Honestly, this is the best way to really get what's going on inside the t-test. It's such a simple but powerful way to think about it. Okay, take a look at the basic formula here. That top part, that's our signal. It's the actual difference we found between the brain app group and the book reading group. It's the potential effect we're trying to find. And the bottom part? That's the noise. Think of it like static on the radio. It's all the natural, random variation in the data that we'd expect just by chance. So, the big question is, how do you even measure that noise? Well, we use this thing called pooled variance. And I know, that formula can look a little scary at first glance. But trust me, the idea behind it is super simple. All we're doing is taking the messiness, the variability, from both of our groups and blending them together into one fair, weighted average. It's our best guess at the total amount of static in our experiment. And here's the bottom line. If the scores inside each of your groups are all over the map, that's high variance. It means you've got a ton of noise. And just like static on the radio, if the noise is too loud, it's going to completely drown out the signal, making it really, really hard to tell if there's a real difference there at all. All right, let's get into section 4, running the test. We've got the logic down, so now let's walk through the actual steps. It's a really clear 4-step game plan that takes you from your raw data all the way to a final decision. This is pretty much the standard recipe for any hypothesis test. Step 1, you state your claims, what you're testing. Step 2, you set the bar. How much evidence do you need to be convinced? Step 3, you do the math, you calculate that signal-to-noise ratio. And finally, step 4, you make the call. You compare your result to the bar you set and decide, is this difference real or is it probably just chance? But hold on. Before we start using this test on everything, there are a few, let's call them rules of the road, a few assumptions we have to make sure are met. The big ones are that your observations are all independent, your data looks kind of like a bell curve, and
this one's super important, both of your groups have about the same amount of noise or variance. Yeah, that last one has a fancy name, homogeneity of variance. All it means is that we're assuming the spread of the scores is roughly the same in both groups. And we can't just guess, we actually have to check this, usually with another little test like Hartley's Fmax, to make sure our assumption holds up. And that leads us right to the grand finale, the final verdict. We've done all the work, we've run the numbers, so what? What does it all actually mean, and why does any of this matter?
You know, it's so easy to get wrapped up in the math, but we have to pull back and ask the single most important question. We might have found a difference that's statistically significant, but is it big enough to actually matter out here in the real world?
To figure that out, we look at something called effect size. And a really common one you'll see is called Cohen's d. The great thing about Cohen's d is it gives us a standard ruler to measure our result. It helps us say, okay, the effect of our brain app wasn't just there, it was small, medium, or large. And that is so much more useful than just a simple yes or no. Oh, and here's another key piece of the puzzle. How many people you have in your study, it matters a lot. The more people you have, the more it helps to quiet down that background noise. And when the noise is quieter, it's way easier to hear the signal and find a real effect if it's actually there. Okay, so let's boil this all down. What are the big things to remember? 1. The t-test is your go-to for comparing the averages of two separate groups. 2. It all comes down to that signal versus noise ratio. 3. A significant result just means the difference you found is probably real and not just a fluke. And 4. Don't forget effect size. It tells you how much that difference actually matters. And I've got one last pro tip for you straight from the source material. It's about confidence intervals. A confidence interval is just a range of believable values for the real difference between your groups. And here's the trick. If that range includes the number 0, then no difference is a possibility, and your result isn't significant. But if 0 is not in that range, boom, you've got a significant result. It's a super fast and powerful way to see what's going on. So, I want to leave you with this final big picture question. A result can be statistically significant, but is it important? I mean, just because we can prove a difference is real and not just random chance, does that make it meaningful? You can find a tiny, insignificant, and real-life effect if you have a massive sample size. So the real challenge for all of us is to look past the p-value and ask the bigger question, does this difference truly matter?